Here's some review problems with extensions to applications. We have the inverse sine, the inverse cosine, and the inverse tangent. Hard one is the inverse tangent. Right? All three cases when I ask what's an inverse trig function of a number, how do you do that? This is going to come up on the test. I'm going to ask you to find an inverse trig function of some number that you should be able to do exactly. We're only able to do these if this is the tangent of a special angle, or in general, the trig function of a special angle, whatever trig function goes with the inverse trig function. And the way you always do these, this is what you need on the test. I always have students that say, you know, I did all the homework and I got them perfect, but on the test I just blanked. I couldn't do any of them. The problem is usually that they did them all, every problem just like the last, and didn't learn to look at a problem and say, oh, this problem I use that method. This problem I use that method, right? If you're making a cake, you go to a cake recipe. If you're making a pie, you go to a pie recipe. That's what you have to do is say, if I'm making an arc tangent, what do? I go to the unit circle recipe, right? So on these things, when you actually have to calculate an inverse trig function exactly, sketch on the unit circle. However, unfortunately, arc tangent is the hardest one. If I said arc sine of some number, then you put sine is the y coordinate, the line of all y coordinates, and that sort of thing that you remember. But for arc tangent, it's a little trickier. What we're asking when we ask for an inverse trig function, though, arc tangent in this case, is what angle has that trig value? I just have to talk loud at the beginning, get him to shut the door so we can leave it open, right? So, what angle theta has this tangent? That's what the inverse trig function is, but it's more than that because there's actually an infinite number of answers to this, right? You can always add rotations and it comes out to be the same. But arc tangent is a function. There's only one answer, right? A function's a rule. You put in a number, you get out exactly one number. What we're asking is what angle between minus pi over 2 and pi over 2 has this tangent? All right, so what angle between minus pi over 2 and pi over 2 has tangent equal to minus 1 over square root of 3? That's all you have to answer in the unit circle. But like I said, this is the tricky one. Here's what you do. You rewrite it as tangent theta equals minus a half or minus square root 3 over 2. Why would I write it like that? Because what you want to do is interpret this as a y over an x. And if I call this y and this x, it's not on the unit circle. Square root of 3 already is 1.7. It's all by itself outside of the unit circle. If I divide these by 2, I recognize square root 3 over 2.5 plus or minus are on the unit circle. So you can just kind of memorize that, divide that by 2 when you see this. Or if you want to see this more generally, how do I know to divide by 2 without just sort of memorizing that this is on the unit circle and this isn't? Here's what happens in general. If you have any point in the plane AB, you have a ray going out through AB, and you say, I wonder what's the corresponding point on the unit circle so I can find the sine and cosine of this angle theta that goes to AB. Remember how to do this? You say this point out here is on a circle of bigger radius, and what's its radius? The triangle is A by B, so the radius here by the triangle is square root A squared plus B squared, right? Pythagorean theorem. And so if I have a unit radius circle, what are the coordinates at this point? The ratio of the radii is 1 to the square root A squared plus B squared. So the point here is in the same ratio, right? A over square root A squared plus B squared. B over square root A squared plus B squared. Right? So if this one, square root A squared plus B squared times as far out goes to AB. So that's the coordinates at this point. It's the rate because of the ratio of the two radii of these circles, the big one and the little one. And so what happens whenever you divide by the root sum square of these two numbers, you'll get a point on the unit circle, except this should be, sorry. Now, there's another possibility too. This minus, you can put it up here, or you can put it down here. It doesn't matter, right? So we can say this is a point on the unit circle, or plus 1/2 over minus square root 3 over 2 is also a point on the unit circle. We can interpret this as y and this is x, because there's also a point over here on the opposite side, right here on the unit circle, that has the same tangent, that has minus a over square root a squared plus b squared minus b over square root a squared plus b squared. And both these points have the same tangent. Any angle here to AB that has a tangent b over a, right? Opposite over adjacent. Also over here, this point over here, if you put minus a minus b, or this one, has the same tangent ratio, opposite over adjacent. The two minuses cancel, right? Gives us this minus a minus b. This one over this one is also b to a on the circle out here. Anyway, so there's two choices, 2 points on the unit circle that have that tangent, one here and one here. Those are the 2 points with these coordinates. Right? So that's what I did. I divided top and bottom by the root sum square. And this is more explanation than you need. You don't need this. Just make this a ratio of points on the unit circle by dividing by the root sum square of these two numbers, right? Plus or minus. Now, which one do we want? Well, if this is y negative 1/2, halfway down, this is x square root 3 over 2. I get a point right here. The other one is plus 1/2 for y, minus square root 3 over 2 for x is right here. And they're always directly opposite. And which one do I want? The arctangent is the angle in the first or fourth quadrants between minus pi over 2 and plus pi over 2. I only have to be in here, so I throw this one out where x is negative and y is positive. That's this one, because that's the wrong quadrant. That's quadrant 2. This one being in quadrant 4 is okay. So this is the one I want. And then I just have to figure out what is this angle here. It's not this one. Why isn't it that one? This terminal ray has the right tangent. Again, the angle has to be between plus and minus pi over 2. I can only go down this way or up this way. This is too big an angle, right? Bigger than pi over 2. So what I want is this angle here. That's the only angle between plus and minus 90 degrees that has that tangent. That'll be the arctangent. And to figure it out, it's pretty easy. I went down to minus 1/2, so this side length is 1/2. This is 1 because it's unit circle. I went from 0 to square root 3 over 2, so this side length is square root 3 over 2. It's 30, 60, 90. This angle is pi over 6, but that's not right. What is it? Minus, yeah, because I did it clockwise. So the arctangent of minus 1 over square root 3 is minus pi over 6. I'll probably give you something like that in this next test. You have to be able to calculate these exactly. And again, if you bought one of those special calculators for math and science majors, I don't know how many of you are going on to math and sciences where you use this a lot. If you take calculus, you'll want it, although you may not be able to use it on the test in calculus, depending on the teacher. You can't use it on the ACT either. There are calculators out there now that will tell you exactly minus pi over 6 rather than a decimal approximation. But I want an exact answer like that, not a decimal test. Don't use in your calculator. When it's not from a special angle, then I'll say, round it, and that means do it on your calculator. But for special angles like this, you want to be able to get it exactly. And be able to sketch a drawing, I might say sketch the drawing and find the angle. So you can't just run it on a special calculator. What happens is later on in the course, you have to do the same thing with other angles that the calculator can't do exactly. And you have to learn the skill now, or you won't be able to do those problems later. All right. So there's that one. The hardest problem for inverse trig functions is the inverse tangent. We don't do the inverse cotangent, cosecant, or secant, even though those exist, because you don't need them in practice. In applications, they're just seldom used. You can always use one of these instead. All right, so there's the first problem. You want to do another inverse sine or cosine? Did we do enough of those? Feel comfortable with it or not? Let's do one real quick. Suppose I had the inverse cosine of 1/2. What does that come out to be? Now you're asking, this is an easier problem. What angle theta has this cosine? So the inverse trig function is what angle has that trig function value. But it's not any angle. There's only going to be one answer. For inverse cosine, remember, it's not an angle in the first or fourth quadrant, it's an angle in the first or second quadrants because of the piece of the cosine function we took to figure out this inverse cosine function. Inverse cosine is the unique angle between 0 and pi, first and second quadrants that has that cosine. So once again, the recipe is you go to the units, you ask this question, the inverse question, and then you go to the unit circle. Cosine is the x coordinate. This is easier. X equals a half is all points with this x coordinate. So I'll draw the vertical line, x equals a half. I think it's easy. Just, oh, there's 2 points on here that have that x coordinate. So two terminal rays. If theta is going to be between 0 and pi, throw this one out. This is in the wrong quadrant. Arc cosine has to be in quadrants 1 or 2. So arc sine and arc tangent, you need the angle in quadrants 1 or 4, minus pi over 2 to pi over 2. But arc cosine, you need it in quadrants 1 or 2. There's that little trick. And that's why I say in this class, it's more practice like a sport than memorization. You can't memorize all this stuff. You just have to practice, and then it comes to you quickly. It's a little tricky. So throw this one out. There. And we want this angle. What is it? Well, it goes out to a half here. This side length is a half. It's a unit circle. This side length is 1. The Pythagorean theorem will force this side. I know what it's forced to because I've seen this before. 1/2 1. This remaining side by the Pythagorean theorem will be square root of 3 over 2. And that triangle has a 60-degree angle here, which is pi over 3. There it is. The arc cosine of 1/2 is exactly 1/3 pi. The only angle whose cosine is a half and the angles between 0 and pi. Arc cosine is a function. There's always only one answer. All right, so that's the difference. It's a little easier with arc cosine or arc sine. You just draw them. Okay, now I want to make sure we have a couple of these down.
Professor,
Yeah.
how did you determine that it was 60 degrees?
Oh, because I memorized the triangle. I memorized this triangle. It fits in the unit circle. 1/2 square root of 3 over 2, 1 has a 30, 60, 90 triangle. So once I see 1/2 on this side and 1 on this side, I know that the Pythagorean theorem will force the third side. The third side will be square root of 1 squared minus a half squared. And if you work that out, it's square root of 3 over 2. And so you memorize this triangle and you know it comes from the 30, 60, 90. We did the proof of that a long time ago. What you do is you draw the isosceles triangle. Maybe this looks familiar. 60, 60, 60, so they add up to 180. Not isosceles, the equilateral, right? Equilateral triangle, all sides the same. Then you drop a perpendicular, and then this must be 30. And if this is unit sides, all the same, then they have to all be 60, so they add up to 180 or equal. Then by symmetry, this must be a half. This must be a half, right? And then the Pythagorean theorem, I told you, forces the other side, the height here, to be square root of 3 over 2. That's the proof of it. And then you memorize this triangle and that it goes in here. So when you see 1/2 and 1, you automatically know the last side from doing the Pythagorean theorem before. You already know the 60-degree angle from this proof. So that's how I figure it. And then they have to memorize 60 degrees as pi over 3. Otherwise, you have to compute it by taking 60 and multiply by pi over 180 every time. That's, that gets tedious. And now, I think, yeah, we're on. If you have trig functions of an inverse trig function or inverse trig function of a trig function, things get sometimes kind of tricky. For instance, suppose I have sine, by examples, where the practice comes in. The sine of the inverse sine of 0.4. You say, wait a minute, that's not a special angle. What do I do when I have a trig function of its own inverse trig function? What should the answer be? Remember these, if you have trig function, inverse trig function, think of this as f of f inverse of x. When does that give you x back? For a true inverse function, it always gives you x back, but we only took a piece of the sine function. That's where this is tricky. It's not an inverse of the whole sine function, so it only gives you back x, or in this case 0.4, if what? If the inverse trig function is defined. So remember that when you say sine of inverse sine, it gives you this back if it's defined, which is for x between -1 and 1. Well, it is. 0.4 is between -1 and 1. So the answer here, it'll be undefined otherwise. Only take an inverse trig function of a number between plus and -1. Try it on your calculator, it'll say domain error, right? So the answer to this one is just 0.4. What if I took the cosine of the inverse cosine of 1.2? Now what do I get? Once again, it's f of f inverse of x. It will give me x back, 1.2 back, if -1 is less than or equal to 1.2 is less than or equal to 1. Otherwise, it will be undefined. So what does it give back this time? 1.2 is not between -1 and 1, right? It's bigger than 1. So if you see a trig function of its own inverse trig function, you'll either get the number back or you'll get undefined. We wrote that on the board before, but it's always harder when you actually have a real problem, isn't it? So I think it is. You see it and it all makes sense, and then you go to actually compute something. Wait a minute. Kind of like watching all those great baseball players this season, right? And actually go to hit the ball, you haven't hit it before. Didn't know how to hold the bat so much. All right. So that's the way trig function of its own inverse trig function works. What if it's an inverse trig function of if it's a trig function of a different inverse trig function, like sine of the arc tangent of 3. What is that? Suppose I gave you that on this next test in a week. 2. This is another cookbook. Trig function of its own inverse trig function, you get the number back or undefined, right? But you just think f of f inverse. That's the way you can. If you try and rote memorize it, you just can't. You have to have some sort of concept here. This one, there's a 3-step method, right? Take the triangle with the inverse trig function you see. In this case, inverse tangent. Right? I'll draw that. And you don't have to draw it accurately, actually. You just have to label it accurately. So I say triangle, I mean right triangle. Trying to be brief. Sometimes we need to not be too brief, though. Right triangle with the theta equals the inverse trig function, you see. So I'll put theta here. If I put theta here, it doesn't matter which place you put it. You just got to label it correctly. I want theta equal arctangent of 3 in a triangle. Theta equals arctangent of 3 means that tangent theta equals 3. They're equivalent for a triangle. So how can I make the tangent equal to 3? The tangent is the opposite over the adjacent, right? So I have to put this over this in a 3-to-1 ratio. It's easiest just to make this one 3 and this one 1. You can make this 6 and this 2, or this 30 and this 10. I like picking the easiest whole numbers I can. Let's put 3 and 1. That's step 1. Make a right triangle with the inverse trig function that appears. Then step 2 is use the Pythagorean theorem to complete the triangle. What is the last side of the triangle? In this case, we're missing the hypotenuse. The hypotenuse is the root sum square of the other sides. This is the Pythagorean theorem solved for the hypotenuse. I told you we'd use it all semester, right? Square root of 3 squared plus 1 squared. Root sum square of the legs is square root of 10. Reduce that if you can. In this case, you can't. So the last side here is square root 10. Now you've got to evaluate by the triangle the desired quantity. So draw a triangle with theta as the inverse trig function. Finish it with the Pythagorean theorem. Use the triangle to evaluate. By the triangle, the sine of the arctangent of 3 is the sine of theta. I made theta that way. Right? But the sine is the opposite over the hypotenuse. Let's see, it's 3 over square root 10. I will take that answer. That's as simple a way as you can write it. However, if this was, when I put it on the key, I will probably rationalize the denominator. Your algebra teacher would prefer that. Rewrite it as 3 square root 10 over 10 is also correct, of course. That's the official algebraic way of writing it, so you can compare them. So either of those answers is fine. Yeah. All that seems fine, but I told you we're extending today. This is where you learned to play t-ball before, and now you're going to actually go out and play a baseball game. You're going to actually hit a pitch. Let me move this over. Baseball, yeah. Particularly baseball over other sports. It's just that season, I think. Just finishing. Well, all right. Let's do a harder problem. This is off the homework. What happens is I claimed over there, I guess verbally at least, that you can take a trig function of any inverse trig function whenever it's defined, actually, exactly by hand. Isn't that amazing? You can't do any inverse trig function by hand, only if it's a special angle. But a trig function of an inverse trig function, you always do exactly by hand. How is that? Because it always comes out exactly with that triangle thing. And somehow doing the trig function of the inverse trig function, you can do it where you couldn't just do the inverse trig function by itself. So here's an example that'll show you that. This is right, getting a feeling for what you can do with this now. Where'd it go? There it is. Suppose I asked you to do, this is number 7, 6.3 supplement. The cosine of the inverse sine x over x plus 1. How about that? You can do all these expertly. You get an A+ on my test. This is the kind of thing I like to ask on tests. How can I do that one? Oh, it's trig of an inverse trig. Go to the triangle, right? That's what I'm saying. You gotta not just do the homework. Make sure you can do them in a mixed up order. That's part of the purpose of the practice exam, so you can look at it and say, it's this problem, I do it this way. It's that problem, I do it that way. Know what you can do with these. Then when you get out in the real world, you'll be able to solve all these problems, right? A lot of these problems are used in lots of things like architecture and construction and all these things. When you're, I'll point that out one of these things later today. You know, when you're building something, you got all sorts of triangles, you know, on the beams and the rafters, and you say, well, if this is 1 and this is 3, what angle do I need to cut this 2x4 at so that it fits right? Right? I mean, you can just set it up in your table saw so it cuts it at the right angle. Here's what you do for this one. Again, it's a trig function of a different inverse trig function. Then you draw the triangle. Triangle with theta equal the inverse trig function you see, even if it's got a variable in there. How about that? This shows that we can do it for any argument here. When we put a variable, we can make this whatever we want, x over x plus 1. All right? Now to do that, here's my right triangle. If I do that for a triangle, this means that sine theta equals x over x plus 1. So I can interpret this as the opposite side, and this is the adjacent, as the hypotenuse for sine x and x plus 1. There it is. The second step is the Pythagorean theorem. Oops. Get the last side. What is it? This time we're solving for a leg, right? Pythagorean theorem solved for a leg is square root of not sum of the squares, but the hypotenuse squared minus the leg squared, right? Root difference of the squares. And here's the mistake a lot of people make. X squared plus 1 squared minus x squared. What's wrong there? I said this before, I think, but oh, come on, they get this to you in your SAT for algebra. You guys all passed, that's why you're here. But they'll do this on the SAT or ACT. They'll say, what is the answer to this one? A squared plus b squared is the first answer, and you quick click on that and it's wrong, right? Because a plus b squared means multiply a plus b times a plus b, and you have to FOIL, right? It's a times a is a squared plus ab is 2ab plus b squared. So, right, I didn't do that. I didn't FOIL. I just squared this one and this one. This is x squared plus, by FOIL, 2x plus 1. Is squaring this out, x plus 1 times x plus 1 FOIL to get this one. Algebra, right? So don't pick this answer, you take the ACT again. I think that's more popular here, the ACT than the SAT still, right? So right, and then minus x squared. So FOIL this one out, and now the x squared and the minus x squared cancel. And I've got square root 2x plus 1 for the last side. All right, 1, 2, 3. 3 is to evaluate by the triangle the cosine, the arc sine of x over x plus 1 is the cosine of theta. I picked theta that way, right? That's here. But the cosine now is the adjacent over the hypotenuse. Let's see, for this, I should have put the angle theta in here. For this angle theta, it's this side, square root 2x plus 1 over this side, x plus 1. And it doesn't even matter what x is. I know exactly what cosine of the arcsine is, provided it's defined, right? And this one will be, right? And this will always work. Because x over x plus 1 is always a number between plus and minus 1. Well, no, not if you put x negative. Anyway, for x positive, it's always defined. All right, so there's how you do that one. Moreover, you can do something a little trickier still. Said this always works, but wait a minute. What if I had the cosine of the inverse tangent of minus 2? Does that work? How can I draw a triangle with a negative side length? There's a couple ways to do this. One of it is to put it into quadrants. I think you'll see the book put it into quadrants, and that works. I like this though. As long as there's not an arc cosine in here, you can do this. Because this also makes an important point out of these things. Note, in algebra, the inverse of any odd function is again an odd function. Do you know that? If I take, in algebra, it doesn't matter, not just trig functions. The inverse of an odd function is odd itself. Kind of see it, right? If you take any odd function, here's an odd function, maybe like this. This might be y equals x cubed or something. All right? Because odd, how do you know it's odd from the graph? Remember? Got this symmetry through the origin. Every point has a sister point over the same distance the other side. So there's an odd function y equals f of x. How do you find the inverse? We're teaching some algebra. You flip it over the line y equals x, interchanging the x and y coordinates. And we're learning some inverse stuff here too. Which means every point that was on the line y equals x flips to itself. And here's y equals f inverse of x. And you notice because these points were symmetric, when you flip them, they're still symmetric. The result is still an odd function. All right, so because it's still got this symmetry through the origin. So that's the graphical characteristic of odd functions. They're symmetric through the origin. And their inverses are automatically odd. That means arctangent of minus x is what? This comes out. Since tangent is odd function, arctangent is, oh, I should put arctangent, sorry. Since tangent is an odd function, arctangent is also. You can pull the minus out. So I'm giving a new property here. Arctangent is odd, you can pull the minus out. Also, arcsine is odd. Not so arccosine. You can still figure out a nice relationship. But even functions, their inverse isn't necessarily even, or it's certainly not odd. So arcsine, the minus also comes out because sine was an arc function. Arcsine is also. That means that we can do an easier problem than this. If you have a negative arctangent of a negative number here, you can pull the minus out. You can say this is cosine of minus the arctangent of plus 2, right? Arctangent's odd, pull the minus out. And now what's the cosine of minus arctangent? Well, that one, how can I simplify that? The cosine of plus the arctangent. Because remember, cosine of minus theta is cosine of plus theta. Use the even property. Cosine is even. The minus goes away. So I can just drop it. Instead of evaluating cosine of the arctangent of -2, I can just evaluate cosine of arctangent of plus 2. Now I can do it. I got rid of those negative side lengths. So you can do this kind of thing if you have an arctangent or arcsine in the middle. And now I can do the 3 steps to evaluate this. 1, let theta be the arctangent of 2. So that equivalently in a triangle, tangent theta equals 2. If I call this theta in a right triangle, for tangent theta to be 2, I want that to be the ratio of opposite to adjacent, right? So I can call this 2 and this 1, or I can call this 10 and this 5, or whatever I want, just so it's a 2-to-1 ratio. Let's make it as easy as possible. Step 2, you calculate the last side by the Pythagorean theorem. For its a hypotenuse, it's the root sum square of these. Square root 1 squared plus 2 squared is square root 5. Well, I label that square root 5. And step 3, I just run to the triangle to evaluate this expression. Cosine of the arctangent of 2, which is also the cosine of arctangent of minus 2, equals the cosine of theta, because I made it that way. But the cosine of theta is the adjacent over the hypotenuse, which is 1 over square root 5. So again, we did it exact. So nicely, we can do any trig function of a different inverse trig function like that. Now, if it goes the other way, it's a little trickier. For now, inverse trig functions trig functions are different, right? So you just have to think, what case is it? For example, if I asked you to use the unit circle for special angles. You get stuck on any of these, try unit circle. Often that's the thing. Most things are solved with the unit circle. You don't just get this nice algebraic formula like you did for trig functions and inverse trig functions. If it's inverse trig of trig, there's not a nice thing that works for all angles, but we can do it for special angles still. And for non-special angles, you just get a calculator approximation. So for instance, if I want to evaluate the arc cosine of the tangent of minus pi over 6, what could that be? I'll just go ahead and calculate it, right? I'll say that's a special angle. I calculate the tangent. Take an angle of minus 30 degrees, minus pi over 6. I memorize that triangle, right? I've got 1/2, 3 over 2, and 1. My memory. Use that all semester. And now, that means the coordinates of the point are, let's see, square root 3 over 2 minus 1/2. That's the x and y coordinates. So I'll take the tangent minus pi over 6, and that's the y over the x. That is y over x is minus 1/2 over square root 3 over 2. The denominators both being 2 cancel. It's the arc cosine of minus 1 over square root 3. And I don't even have that, so I just leave, this is as far as I can go, unless this comes from a special angle. At this point, I have to use calculator, since minus 1 over square root 3 isn't from a special angle. And our tangent of that, or our cotangent, sure. Not so good going the other way. Nonetheless, if it happens to be an inverse trig function of the same trig function, you can deal with it. Same trig function. Just use the unit circle again. And suppose I, for instance, had the arc sine of the sine of 0.2. Wait a minute, that's not from a special angle. Can I do it? I can, and I still use the unit circle. That's one way to do it, at least. What is it supposed to be? If this is a true inverse, this is f inverse of f of 0.2. I ought to get 0.2 back, right? Is that right? Inverse trig functions are more difficult because they're not true inverse of the whole function. They're only an inverse of the part of the function. So remember that you have to memorize the rules for this. For inverse sine of a number, it gives you that number back when? When that number is between minus pi over 2 and pi over 2, when it's on the piece of the sine function that we inverted. So I'll give you that back, and I'll give you something else otherwise. So just like trig of inverse trig of the same function, It'll undo it in some cases, but for trig of inverse trig, it would be undefined. Otherwise, this one, you can get a different angle back, actually. So here's arc sine of the sine of 0.2. Oh, good, 0.2 is between these, right? Pi is about 3.14, so this is a little bigger than 3/2. 0.2 is between minus 3/2 and 3/2. Check, it's that one. I get 0.2, easy as that. So again, if inverse of f of 0.2 is 0.2. Unfortunately, when it's inverse trig of trig, it's not undefined in the other cases. You have to figure out what it is. So here's A, B. Suppose I said, what is the inverse cosine of the cosine minus pi over 4? How about that? Fortunately, it's a special angle. I can calculate it exactly. But nonetheless, what I'm going to get this is equal to minus pi over 4. I can just write the answer immediately. If minus pi over 4 happens to be between 1 and what? Arc cosine is different, right? We inverted a different piece. Arc sine undoes the sine when they take an angle in the first or fourth quadrant. Arc cosine undoes the cosine when you're in the first or second quadrant. Uh-oh, this angle isn't there. We're going to get the something else case. Right. So this time the angle's not in here, we get the else. How do we evaluate else? If it comes out to be the else case, you have to do it on the unit circle. And here's what you can do. Draw the angle minus pi over 4. It splits the axis here, right? Minus 45 degrees. And say, what is the cosine of minus pi over 4? Well, we memorized this other triangle, right? For a 45-degree angle, 45, 45, 90 triangle, the side lengths are square root 2 over 2, square root 2 over 2, and 1 by memorization. So the coordinates of the point are square root 2 over 2 and minus square root 2 over 2. And then the cosine of any angle is the x-coordinate of the unit circle. So now I'm going to say arc cosine of the cosine of minus pi over 4, just from the unit circle, is the arc cosine of square root 2 over 2. All right? Because I can evaluate this as the x-coordinate circle. Now what's the arc cosine of square root 2 over 2? That's our first problems we were doing today, right? Evaluate an inverse trig function. You sketch the unit circle, you already have it. And what you want is we want theta between 0 and pi for the arc cosine function, such that it's the inverse trig function problem, such that cosine theta is the given number. Huh? That's what the arc cosine is, the unique angle between 0 and pi that has that cosine. That's easy. I draw all x coordinates equal square root 2 over 2. That's this vertical line. X equals square root 2 over 2. And I notice the ray I have is an answer, right? That one right there is possible. But there's another one up here, right? Another point of the unit circle that has it. So which one is it? Do I want this ray or this ray for the terminal ray to evaluate the arc cosine of square root 2 over 2? It has to be between 0 and pi, right? What's this one? I throw out the one that the original one. If I pick this one, I just get right back the number I put in. It's this angle here. Well, by symmetry, since I've got a congruent triangle here, this angle, this also has to be a 45, 45, 90 triangle, just with a positive angle here. So the answer here is pi over 4. And that's the unique angle with the same cosine as minus pi over 4. So the arc cosine of the cosine of minus pi over 4 is not minus pi over 4, it's actually plus pi over 4. That's the something else in this. The inverse trig of trig is harder. Sometimes you get the same number back. Sometimes you have to sketch the unit circle and figure out, which angle, this is asking which angle has the same cosine as minus pi over 4, but is between 0 and pi. That's what we did. We found the angle between 0 and pi with the same cosine as this angle. We're going to do a little bit more with that in later chapter. For now, that's all we're going to do. Getting complicated. End of the chapter is always complicated. This is where I should have a joke or something. In my sock puppets, I don't know. Anyway. So now what we need to do finally is some applied problems. That's all the hard stuff. We just want to do some applications. And the same comment on applied problems works as before. How do you solve an applied problem in trigonometry at least? Since it's normally geometrical, the first thing we do is draw a picture. All right? And in that picture, we mark all the given numbers, angles and side lengths, and the desired ones we mark as variables, x or h or p or something like that, depending on what's appropriate for the picture. Then we go through and we look and we mark any obvious consequences, right? If they've got two sides of a triangle, we can complete it with the Pythagorean theorem. We got supplementary angles, right? We can take 180 minus the other one. Mark any obvious consequences that might apply. Some of them are not useful. Then 3, hopefully you get a problem that you can write as an equation. You solve these by inverse trig. Other section will be solved by some other method. But in this section, it sets up an inverse trig thing, just one of these methods we already did. So it's the same things we already did, but first you got to draw the picture and mark any additional consequences. That's it. And I'll show you, if you look online on the practice problems I wrote on there, 2 of them were like these. I didn't try and get real creative on those, just want to make sure you practice the same kind of stuff mostly. But there's a lot of creative problems you can produce out of this. And here's 3 of them right in the back of it. This will help you finish your homework. The homework is to finish all of chapter 6. Finish 6.3. What I did in chapter 6 is I said all but the last problem out of 6.1, all but the last problem out of 6.2, and all of 6.3. All right, out of the supplement. Be able to do those kind of things. It's only one chapter, right? You can keep a cookbook memory for this for one chapter, right? So it'll be easier than 2 chapters last time. Now let's try this one then. This is number 9 out of 6.3. A 13-foot ladder. Something like this before. Leans against a building. Pull my pen out. I must be working too hard today. Leans 12 feet up a building to the 2nd floor window. Find the angle it makes with the ground. Oh, I'm sorry. Find the angle it makes with the building. It's not required to draw a picture, actually. If you can figure it out and get it right, I'm fine with that. I'll just say, it often helps me a lot. So let's try it. Here's the picture. Always assume the ground is horizontal and the building is vertical unless the problem says otherwise. So here's step 1. Draw a 13-foot ladder. up the building, which is vertical. That's 13, and it goes 12 feet up the building, so there's the given numbers. Now I can put in all sorts of other numbers, I can put this length, but I may not need it. But I am asked to find the angle at the building, so I'll mark that theta. Here's the two number I'm given, here's the angle I want to find, so how do I find that? You look at the picture and you say, I know equation relating those two. Here's the obvious consequences. Let's see, here's the adjacent side and the hypotenuse, so that's cosine. The obvious consequences of the cosine theta is 12 over 13. Right? Now I solve the inverse trig function. How do I solve that? In a triangle, trig function equal to number is equivalent to theta equals the inverse trig function. Or a triangle. You can do this. So now we can run that in the calculator. The problem says to do this in radians. I kind of like degrees because when I see it in radians, I can never figure out, you know, is that a little angle or a big one? You have to think a long time. You can, but it just, you know. Well, again, on the calculator, do an inverse trig function. Remember, you push second trig function, right? Second tangent to get the inverse tangent. 12 divided by 15. Since this is not a special angle, you can't do it exactly. You might have to close the parenthesis here in the calculator, depending, and then push enter to evaluate it. What appears on the screen, of course, is arc tangent. Those are the buttons. Arc tangent parenthesis 12/13. And then it gives you this arc tangent. Make sure it's in the mode you want. And I get 0.74 54 and a bunch of other things. All right, so there's the 4 digits. I don't know how many the problem said. So there's some radians because my calculator is in radians mode. If you let your calculator in degrees mode, you get this times 180 over pi. You get 42 degrees, 42.7 degrees. Degree mode. That's not right. I do. This is where it's good to do the sanity check. That doesn't look like an almost 45, 45, 90 triangle, does it? What'd I do? Just entered something.
You make a negative tan instead of.
Oh, I'd use arc tangent instead of arc cosine. Yeah, this is cosine, so it's arc cosine. So there's the mistake, right? Arc cosine. Now I'll do the same thing with cosine, first cosine, and hopefully get it right. So use the sanity check and check your answers. Now let's see what I get now. Arc cosine of 12 divided by 13. And I get 0.343948 in radians. For a sanity check, I convert it to degrees times 180 divided by pi. Gives me 22.61 degrees. That sounds more reasonable. There's how you can do a applied problem, just to draw a picture and put in the obvious consequences. It should give you a problem of the kind you've already seen. That's sort of intuition you have going into this. All right, the next one then, number 10. Well, you have an isosceles triangle. It's an isosceles triangle. Do you remember that from geometry? Two equal sides and equivalently two equal angles. It has two 9-inch sides, yeah, two 9-inch sides and an 8-inch side. Find the angle between a 9-inch and 8-inch side. How about that? So step one, I draw the isosceles triangle, two sides the same length, 9 and 9. The other side is 8, a little shorter. Right? I'm trying to find this angle theta. Right? So I draw on the things I know and the thing I'm trying to find. Also, this is theta if you want. That's the obvious consequence. Isosceles triangle, these two have to be equal. What other consequences do I have? I should draw that in red. These will be the consequences. How am I going to find that angle? It's not a right triangle. Right? I figure I know how to do right triangles. I have to make a right triangle. How do you? There you go. Perfect. Yeah, split it down the middle. Just drop a perpendicular by symmetry. Since these are both theta now, I use my consequence here that by symmetry. This has to go right down the middle. That leaves this length is 4, and this leg length is 4. I've got a 4 by 9 right triangle with theta in between those sides. There's the consequences. So now for problem 3, the object is to find theta. Right, the relation between these now, again in here, is the, well, it's adjacent hypotenuse. So I'll say the cosine of theta is 4/9. So for part 3, I say solve this, theta equals inverse cosine of 4/9. All right? And I just have to calculate that. Since it's not from a special angle, 4/9 doesn't come from a special angle. Just looking, is it square root 2 over 2? Is it a half? Is it square root 3 over 2, 0 or 1, or minus any of those? Then it's from a special angle. Otherwise, you just run the calculator. So inverse cosine, this one wants in degrees, so I'm going to put it in degrees mode. Got it, right? Degrees mode, if I push inverse cosine, 4 divided by 9, I get 63.6 degrees. And then you do the sanity check. Does that seem reasonable? If it was an equilateral triangle, 9, 9, 9, these would all be 60, right? 60, 60, 60 makes 180 degrees. A little bigger than that when this end one is shorter. Yeah, that looks about right. So that's probably correct, right? Sanity check is which way is the wind blowing. Just put your finger in the mouth and hold up. I think a storm's coming because the clouds are there and the wind's, Anyway, so it doesn't check it, but it, it gives you a good guess. There's that one. Looks right. Finally, the last problem on there. Oops, let's see, there we go. Kind of a tricky one. Line. Y equals minus 3/7 x. To the origin of the xy plane makes what angle? With the negative x-axis. What does that mean? This is where the picture shines, right? Because it's kind of hard to figure it out from the words sometimes. So you draw the line. How do I draw a line? Right. Y equals minus 3/7 x. This is y equals, right? If you put it in slope-intercept form, y equals mx plus b. M is the slope. B is the y-intercept. Well, this is in slope-intercept form, right? It's y equals minus 3/7 x plus 0. The y-intercept must be 0. The slope must be minus 3/7. So I draw it through the origin with slope minus 3/7. So I could consider this the rise of minus 3 when the run is 7. Or I could say it's rise of 3 when the run is minus 7. Let's try it this way. Rise of minus 3. So 1, 2, 3, 4, 5, 6, 7. I scale these equally, but there it is. So if you go through the point 7 minus 3, then that'll give you a slope of minus 3/7, and then it goes back this way also. And the question is, what is this angle here, theta, right? Now I see what I'm trying to find. But it goes through the origin because the y-intercept is 0. And then it has slope minus 3/7, so it goes over 7 and down 3. Right? That's one way to sketch it. Or just plot 2 points and put on your straight edge, but it goes through the origin. Right? Step 2, you do any obvious results. Well, suppose I finish the triangle here. I'll make this triangle. And I observe that this angle here, theta, is the same as this angle here, theta. Right? We're just asking for the positive angle, theta, between the axis and this. And we usually say it's the smaller angles. You might say, oh, the angle is this one, right? Well, usually we say it's the smaller of the two angles between the two lines is the angle between the lines. We'll say it's this one, but by symmetry, it's also this one. And in this triangle then, I notice that this side is 3 because it goes down to minus 3. This one is 7, goes over to 7. So I've got the opposite and the adjacent. I notice in the obvious consequences, tangent theta is equal to 3/7. So use that symmetry, use the triangle, and get that. Now, by inverse trig, we can solve that, right? If tangent theta equals 3/7 in a triangle, right triangle, theta must be the inverse tangent of 3/7. I can just run that on the calculator. I think it says radians on here, but I always like degrees better. I can see if it looks right. We'll put it in radians though. All right, change the mode again. Mode, radians. But it worked. Second tangent, 3 divided by 7 gives me about 0.4049 radians. You don't need to put in the units when it's radians. It's assumed unless you put a degree on there. So there it is, about 0.4 radians. I don't know how many digits they rounded to in the answer page. Okay, well, that finishes all the difficult problems there. Any questions, any other things you want to try for today? You can do that, you can do them all. I don't want to start a new section here because 5 minutes, I'm always going to have to just repeat them the next time to get you back up to where you were. Well, maybe I should just leave it there then. Finished chapter 6. Bring questions for next time. We'll review the past. I'll let you go 2 minutes early. Have a nice rest of your day.